Good afternoon, everyone. My name is Pradeep Kumar, and today I'm going to present my work on GraphOne. It's a data store for real-time analytics on evolving graph. So graph is almost everywhere. It's a basic building block for a number of applications, such as modern trade applications like social media, navigation, e-commerce, and a number of other examples. Just to give you a very brief example, the friendship network is one of the most important components of the social media. On the other hand, you can also think graph as a metadata store for big data. So assume that you uploaded a picture on Facebook. So that itself is a meta information. And then on top of that, few people might comment on your photo, may like your photo, or like some automatic tags, like you may want to tag your friends, or like when the photo was taken. All these are meta information that is part of the photo's characteristic, the relationship, that photo with the user. So when you have such kind of relationship, graph generally becomes more important as they can easily express this kind of storage very easily. Scientific applications are also using a lot of graph data to store their information, such as protein-protein interaction network or metabolic network, as you can see in this diagram. There are a number of other applications. People are now using graph analytics to find vulnerable piece of code, such as buffer overflow, by just writing graph queries, or even trying to find if there's a cyber attack on your enterprise computer network. Knowledge graph is, again, very important, and so it's important for GDPR. So before I start my techniques and all that, let me define certain terminologies, which I'll be using throughout this talk. So if you need to perform an analytics on the whole graph, like take a snapshot now and perform few iterations, I generally call that a topological graph. And those analytics would be called batch analytics. So for example, finding an articulation point in a data center computer network would be one batch analytics example. Or so could be like PageRank, breadth first search, which people are now using as a very standard graph benchmark. On the other hand, there's also something called streaming graph. So consider the same computer network graph, but now instead of computer and switches being the node, here the nodes are more dynamic in nature. Example could be computer plus port information, user information, process ID, and things like that. And the actual edges could be the network flow information, like how many packets are arriving each second, or something like user authentication logs or process events and many other things which are very dynamic in nature. So topology will change very frequently. And then people are generally interested in some sort of time window, like can you give me the topology for the last 1 hour or last 1 day or last 1 second, things like that. As you can see in this diagram, showing a graph after time t and in the red color. So those kind of analytics or like people generally call it stream analytics, and one example was finding the security risk in enterprise network. So having said that, there are use cases that require that we need to perform all of these analytics together on the same data. So can we do that today? The answer is no. I have classified all of the existing work in different categories, as you can see. And one thing to note here is that all of these systems have very specific kind of ingestion type and very specific kind of data access pattern. To give you an example, graph databases will only support fine-grained ingestion, that is one edge at a time. And they will only offer you data from the whole data. So if you want to some other data, you need to passively run a query to find out some subgraph or things like that. But if you want to perform analytics, which is fine with the batched update, this graph database is going to be very, very slow. That's why you don't do analytics on databases. Same is also true for other kind of systems where they'll either provide you fine-grained ingestion or coarse-grained ingestion, but not both of them together. On the other hand, they will only provide you data access from whole data or streaming access from a time window, but not all of these together. And that's why we want to achieve in this particular work. So maybe you can achieve the same if you are willing to integrate all of these systems together, but there will be a problem that each of these systems have a very private data store because of their kind of ingestion that they support. So if you integrate all of these, you have private data stores storing the same data in a different or slightly different format, so you have very excessive data duplication. And the performance is not going to be very good because one of the component which is going to perform slowest will determine what will be the performance of overall integrated system. So what is our idea is that previously, since people take their data store as very private, let's take it away. So instead of having this kind of figure that you see here, let's separate it out and make the graph data store very separate from the analytics. So people writing analytics should be able to use the same data store for all different purpose, whatever they want to do. And that's what today's work will talk about. And when we do that, it is not only provide you very simplicity and efficient storage format, but it is also faster than a number of competing solutions that I'm going to talk about. Right? So let me give you a brief overview, and then we'll come how the system may, like how can you really abstract the data store away from all these space-like system. So very brief introduction about one format of the graph, which is called edge list. If you know a little bit of databases or NoSQL, you're generally aware of a log. Generally, you do a sequential write, and sort of you are done with the ingestion. So you can see edge log or edge list is entirely this log for the general purpose ingestion. On the other hand, you also have some indexed data structure, which you use to perform query or analytics very fast. So that is the adjacency list. Here, the data would be stored by, indexed by the source vertex, and that is what you see here. So answering a query like what are the neighbors of 4 would be just one lookup, the 3, 1, 2, and 5. But answering this query will not be possible if you use edge list format, right? So in case you are a little bit lost with these two things, just think one as a log and another as indexed data structure, which is true in any databases or NoSQL structure. So our idea is because these two are a little bit complementing in nature. One is very fast for ingestion, another is not so fast. One is very fast for queries, another is not very fast. So there is an opportunity if you are willing to combine these two and trying to understand all of those different access patterns that we talked about a few slides back. And then you can have a system, something like that, that will always, you can do ingestion at very fine granular level by just writing it to the log. So idea is to you always write it to the log, and that's it. And we move the data from the log to the index data or the adjacency store only in the batches. What is the advantage here? Your ingestion is always fast, super fast, because you're not writing to the adjacency store directly, but adjacency store is ingesting at coarse granular level. So there's lots of opportunity to do the optimization. But what we offer really, and the main crux of the idea is this, that now the analytics have the opportunity to choose what kind of data ingestion they are willing to see. And that's what we call data visibility. That is, if you're only interested in bulk ingestion, you can only access the adjacency store and your analytics would be super fast. But if you're willing to, or if your analytics require that you also access the latest fine granular ingestion, you may have to use both of these store because some of the data may not be immediately available in the adjacency store. So that is the main idea. This is a very simple idea, but it's very powerful because this is the first sort of thing that actually lets the analytics choose by saying that if you are fine at coarse granular level, you will be very fast. You don't have to have any performance degradation because of fine granular analytics. And only those who need to access fine granular ingestion, they would be one who needs to trade off little bit performance because accessing from the log is slightly going to be slower. But then this is also very complex because the analytics have to do very complex programming, accessing data from adjacency store and sometimes from both, depending on what data visibility they choose. So we go a step further and do propose a new sort of APIs we call GraphView, which is sort of a logical view, not exactly a physical view, which means they'll access the data from the same two places, but it will give you very uniform access pattern, very uniform APIs because the way we designed the API. So that is called GraphView, and I'm going to discuss how to implement that. So that is actually main idea of behind this paper. Very simple construct called data visibility, and then proposing a GraphView, and then I'm going to discuss how can you use GraphView in the same data to support different kind of analytics. So possibly different kind of ingestion is done, but let's discuss how it can support different kind of analytics. So this is one very simple animation. I'm going to show how really ingestion works. So as and when time arrives, data will arrive in the log first. And let's say you decide to create a snapshot in the adjacency store. So you simply do this. Now all of the data has moved to the adjacency list, while at the same time, some new data might arrive here. Okay? And then while happening this, you again want to create one more snapshot, and then you create one more here. And in the same time, you might have few new edges arrived, which hasn't moved to the adjacency list that are called non-archived edges, as you can see here. So the idea behind this thing is that you can create many snapshots at coarse granular level in the adjacency list, the way because the degree node behaves. So you can see you still have the access of the older adjacency list snapshot Because if you see the number here, 1, which means you only access these green colors thing, you have the old snapshot ready. And if you are willing to access the numbers that are in blue, you have the access of the latest snapshot. On the other hand, the non-archive edges that you see are also very quick because they are sort of fine granular snapshot that you can see. If you remember those two edges, that's it. You have the snapshot almost on free basis. There is some complexity in the deletion. That's how we handle them. We treat deletion as an append operation through some some technique called tombstones. You can see here the negative number at the time T7 that is there. That basically tells you that this data is a deleted data. And also you see the number -1 in the adjacency store. That data is basically tells you that the deleted data lies at the index 1 of that particular edge array. So overall, we will be able to support a number of views. Let's first discuss the static view. So the static view is used for batch analytics. You want to create a snapshot now, which can easily be created because there is snapshot exists from snapshot, which is slightly older, and new edges, the non-archive edges. So you just copy the non-archive edges and the latest degree array, and you have a snapshot very much ready, right? So API are very simple. You just create a static view, pass certain flag like data visibility, and that's it. And then you can use vertex-centric programming model, and you can easily implement BFS, PageRank, or articulation point implementation. By just calling two APIs, get neighbor degree and get neighbors, it will give you the number of edges for each vertex very sufficiently. Now coming to the static streaming view, the generally analytics run this way. You want the latest snapshot now, you run certain incremental compute, and then you again ask for the new snapshot and repeat the incremental compute. So the idea here is that streaming view is nothing but a moving static view. And that's what if you call update view API, you can easily get the latest snapshot and you repeat the incremental compute. While some analytics may be interested in finding which all vertex changed, we also provide that because we have internally the degree information. So if degree information changes, we know there is an activity for this vertex, and that would be in the list. But important question here is, can we provide the streaming view over a time window? And that is a tricky question. And we want to provide that from the adjacency list, not from the edge log, because adjacency list is going to be indexed and much, much faster. So we can do that if you, again, understand the role of degree array in more detail. Specifically, degree array tells you start from the beginning and go as far in the edge array as the number tells you. So if you have two degree array, one will tell you the starting offset and another will tell you the end offset, then possibly you have some sort of a time window from the edge array, and client can easily access that by using the same API of vertex-centric programming model. So that is the idea. We still have the same data structure on the memory, but you can have different kind of access pattern, including fine-grained ingestion access or access from in the like coarse granular thing, or streaming view access, or the access for batch analytics. So once we are done with that, any system researcher go and optimize all of these operations. So one opportunity we have is we move the data from edge log to the adjacency store in bulk. So there are a number of things we can do. A naive operation may be able to do that, but they need to use lots of lock or atomic instruction. What we do, we use very simple technique called edge sharding. Classify all of the edges in a different ranges, like called local buffer in this diagram, and then you can independently run the archiving phase without needing any atomic lock. So that is the idea, and obviously you can see that we'll be able to do much faster than a lock or atomic instruction based solution. And this will also lead to very good scalability because there is no atomic instruction or lock available here. So that is the first optimization. Second optimization is for the memory usage. Because the edge log is circular in nature, there is not much memory involved with it. It's just the problem how much edge log should we have, and we have actually answered that in the paper. But they are not the one which consume a lot of memory, and not so the degree arrays, because we'll only have few degree arrays, and whenever we create a view, we copy those degree array to a private buffer. So you can always recycle those degree arrays. So this leads us to the sum of the memory overhead in the edge arrays, as you can see here, because there's so many links that get created. So the idea here is, so let's see some of the numbers here. So for a graph which have 4 billion edges, the memory requirement would be almost 150 GB if you use this GraphOne at this stage. But if you are willing to convert all of your data at one shot, that's what generally static graph engine does, the requirement is only going to be close to 34 GB. So we have an opportunity to reduce the memory requirement here, and we propose two new techniques. One is cache line size memory allocation, and another is hub vertex. Cache line size is very easy because we are moving data and at batched way, like a number of edges together. We sort of know how many edges each vertex have. So based on that, we go to the next cache line and allocate as much memory as this needs. So it could be one cache line, could be two cache line together, or even more. So this leads us to a number of links reduced, which leave us to very good performance improvement of almost 3 times, reducing the memory to requirement to just 47 GB. And the next is allocating at the 4 KB boundary if those vertex are hub vertex. Like the vertex which have a number of activities, generally like Obama in social media or something who will have so many followers. But their number are very small, that's why memory optimization is also a little bit less. But overall, we are able to do much better and almost very much comparable to the static engine, just 1.5 times, less than 1.5 times memory requirement. And average chain is just 2.47, so which is really nice, we believe. And this optimization is not only for reducing the memory, but it is also applicable for archiving rate as well as certain analytics because the memory is now aligned at cache line. So all of these access is going to be very fast because cache coherency will not come into the picture at all. So once we have done these two optimization, we wanted to find out what should be the combination of these hybrid store. How many edges should be batched before they move to the adjacency store? And as you can see in the x-axis, we have all these different numbers of the edges in the edge log. And the red line, the red vertical line shows that if you have 2 to the power 17 edges in the edge log, the analytics performance doesn't suffer a lot. So we take half of its value because batching will overlap with the archiving, and that 2 to the power 16 edges is what we call archiving threshold. So anytime you have more than 2 to the power 16 edges, it will start the process of moving data from edge log to adjacency store. And that actually gives us close to 43.68 million edges for this particular graph, while I have also listed in the table some other ingestion rate, which all are almost close to 43 million edges per second archiving rate. And only problem is LNL, which is a weighted graph. It has 32 bytes as weight, so obviously it will be a little bit slower than the plain graph, which doesn't have any weights. On the other hand, there's also a logging, which runs very fast. Because of the fast logging, we will be able to ingest even faster than what we claim here. Because the logging rate is sequential, right? The data can arrive at 80 million edges per second, and you will be able to support a higher ingestion temporarily as well as permanently, because an archiving threshold will also increase, not only like it will stay 2 to the 16, it may go up to higher value. Like if it goes to 2 to the power 20, you will have much higher ingestion rate, close to 60 million edges. So you see that it's a very dynamic graph, can easily ingest at much faster rate. But then side effect would be that analytics will have to suffer a little bit because they'll find more edges in the edge log, which hasn't moved to the adjacency store. Okay, so then we are comparing against some of the dynamic graph systems. Stinger is possibly the only analytics system which ingests at the fine-grained update. They directly move the data from the user to adjacency store. They don't have an edge log concept, which means they update at very much smaller granularity. And because we do batching and cache line optimization and all that, we are able to perform more than 5 times ingestion and also faster for BFS and page rank. Same is also true for the graph databases, which was obvious considering graph database offers you strong serializability, very strong data consistency, while we only provide you snapshot isolation using MVCC. So we are almost 2 to 3 orders of magnitude faster. So if your application doesn't need strong data consistency, possibly you should go for GraphOne and use it for very high ingestion as well as ability to perform analytics. Then we also wanted to compare against the static graph engine. Like static graph engine is the ideal world for us. Can we do as good as the static graph engine? So result here shows that we compared against static version of GraphOne, which first we measured against Galois, and we were able to perform similar. So because Galois is a little bit outdated, we wanted to conduct experiment against the static version of GraphOne. And we show here that we are only 17% less performance for real world graph, which means if you have data management requirement, then you only need to suffer by 17% and not more. And that is pretty much okay, considering you are getting the data in a format that most analytics requires, while the static engine generally have a cost associated with something called pre-processing. And you can see that pre-processing cost for BFS is like almost 34 times of BFS cost itself, which we'll avoid completely. So overall, we are actually better than static graph engine on absolute term, okay? So, but even if you don't want to have so much cost, like 17%, the only problem is the link that actually reduces the cost. You can actually compact them later if you want. And that cost is going to be much, much smaller. I'll suggest you read the paper for the analysis on compaction rate when we remove the links from the edge list. So this leads us to the conclusion of this talk. We sort of proposed a very unique kind of abstraction, data visibility, where data is always going to be ingested at fine grain, but it is the analytics who choose what they want to see. And in order to simplify the programming, we propose a GraphView abstraction, which can give you data access from the same physical data, but in a different format. That is what your analytics may require. And we have shown that results are very good compared to graph databases and Stringer both, as well as very much comparable to static graph analytics engine. And one last point is actually you can use GraphOne for your normal use cases where you do not necessarily have input as a graph format. You can use text data or any JSON data or XML data or CSV format. And we have the capability to convert those to the graph because we have written a number of plugins. So in case you need to have real data which have lots of different kind of weights, possibly GraphOne is very much comparable to normal graph databases capability. Right? But we do not have an analytics engine or graph engine query. So if you need to do certain query, possibly we need to do further development and integrate it with GraphOne. Or I can basically choose some other analytics engine and do the integration myself. So with all that, I would like to thank USENIX and NFS and my university for supporting me in doing this research. And I would be willing to answer any question that you might have. Thank you.
Hi, great talk. GraphOne seems like a very good system for continuous or incremental queries. Have you thought about plugging into a incremental sort of query or continuous query, and how would you do that?
The last word, continuous, you said something greedy?
Continuous and incremental queries.
Queries?
Yeah.
Okay, that's what GraphOne is built for. But right now, it is only a data store, like a storage engine. I think if, let's say, Neo4j is online, we may be able to integrate with them, but obviously it requires much larger effort, and alone is not sufficient. So academician, we're mostly interested in the concepts. But I mean, if we have manpower, we can definitely do that. So we are sort of writing small plugins based on our internal use cases, but it won't be able to support very generic, like ad hoc queries at this moment. Yeah.
Thanks.
Sure.
Yeah. With a lot of real-world graph update workloads, oftentimes we have to check whether an edge already exists before we insert a new edge. Do you do this kind of check in your ingestion test?
We don't do that. So our model here is that there would be log changes that would be arriving from the real-world deployment. And since those log changes will arrive from certain front end, which already be doing these kind of checks. So when they insert and they know whether it's a duplicate or not, then they will be sending to us. So we have that kind of information here. Yeah, so we don't do checks.
Thank you.
Yeah, thank you.
If I follow up, what would happen if you need to check the edge first? In terms
So
of performance?
checking would be very fast if we only check in the adjacency list. But checking in the edge log is going to be a little bit costly. So there could be a number of alternate possible that let's not check in the edge log, but only check it when actually we move it to the adjacency store. So because of our edge sharding, edges move in order to the adjacency store the way they have arrived in the edge log. So once we move, next time anyway we insert in the adjacency store, we can actually check. And that check is actually there for deleted edges right now, because we need to find out the deleted edge, because we stored the index, as you can sort of see here, right? The negative numbers. So in order to find that -1, I need to sort of traverse and find out, oh, the 4 is actually at index 1. So we sort of do this check, and I think we can do similar thing. And we have results for weighted graph. So it is not like 50 million or 40 million. It's like 18 million edges per second, but it's 8-byte vertex and 8-byte weight. And the 40 million, 50 million was like 4-byte vertex, that's it.
Okay.
So I believe we will be able to perform almost similarly.
Right. Okay, I'm Chuchao from U of M, and I have one general question. So in your list store GraphOne, do you have a large cache layer there?
Okay, we do not have a cache layer as of today. Everything is in memory today. What we have in the disk is only the logs.
Okay.
So which means if you really have large data, this system is not going to be very useful at today.
Okay, which
so
means it cannot support
very large, yeah. It can support in few use cases that is discussed in the paper, like for streaming graph, if you're not interested from the data from the day one, rather you're only interested in last 1 hour, last 1 day. And if that data fits into the memory, we have a technique where we sort of remove the older edge arrays and just store the latest, let's say 1 day or 1 hour's data. So if your working set size fits within the memory, this system can support that.
Okay, I've got your idea. So, which means if I want to support a very large graph, like Twitter or Facebook, I need other system to store that, and then later be retrieved out to insert into this graph store for the only analytical processing purpose.
Sort of. You're almost correct, but this system won't allow you to do that because we don't have sufficient memory to store that data at once.
Okay.
So if that's the point I said, like working set size. So if you're interested in the whole data, then answer is no. But some cases like streaming data, like you want to see the click stream or the like stream for 1 hour, then if only 1 hour data can fit in, we sort of remove the older data from the memory and make available space for the incoming data. So that could be possibility.
Okay, thank you.
Yeah, thank you.
All right, let's thank the speaker one more time.
Okay, thank you very much.